Welcome to the next episode of solving section 7.5 in the James Stewart Calculus Early Transcendental textbook, the 7th edition. We are on number 27. So let's continue. We have this integral dx over 1 plus e to the x, okay? How can we solve this? Can we substitute something here? Like if u is 1 plus e to the x, du would be e to x dx. I don't see that signature, or e to x dx anywhere here. So maybe not that. So I probably do want to substitute something relating to e, but the problem is there's no e on the top because the derivative of e is e. So I probably want e to be somewhere on top and also on the bottom. So let's kind of make a hack of multiplying both the top and bottom by e to the minus x. Why do I want to do that? As I said, I want the top to have a e to the x or something like that, e to the minus x. That doesn't quite matter. So we can have a signature of the derivative at the top, actually, to hopefully make a substitution. Okay? And actually, when I do that, the bottom can simplify. It'll be the top remains the same. Okay? When I distribute this e to the minus x to both terms, I get e to the minus x. What's e to the minus x times e to x? Remember properties of exponents, when you multiply them together, you can add the powers. So it'll be x minus x, which is 0. So e to 0 is 1. So it'll be plus 1. And now I can make a very nice substitution. U is e to the negative x plus 1. Du would be negative e to negative x dx. Okay, so I'm going to continue the integral over here. We would get negative du over u. Okay, this is just negative log of absolute value u plus c, which is negative log of e to negative x plus 1 plus c, and that's our answer. Quite simple, actually. So the trick here was, in order to make a substitution, I need to have some term with e on the top, or e to x, something like that on the top. And how to do that? Oh, I decide if I multiply by e to negative x, the bottom becomes something nice, like this, which I can substitute. Okay. 28. Integral sine square root of at dt. How would we solve this? I'm assuming a is a constant. Okay. So maybe let's use the trick where it's a composite function. So let's make a substitution. Okay, because maybe let's also go through all the techniques. So I was just saying substitution. How about by parts? It wouldn't be very nice because it's sine of square root at. So even if u is that, du would be cosine of square root at times derivative of the square root term, which makes it kind of messy. So maybe it might work, but I kind of don't want to do that. Okay. How about trig integral? Well, it's usually like sine to some power of t, cosine to some power of t. So it's not in that form. Trig sub is not something squared plus something squared, so probably not that. Clearly it's not a rational function, so not partial fraction decomposition. So let's try the idea I was thinking. Let's make a substitution. Why don't we let u be square root of a t. And remember, instead of differentiating u, we can say u squared is at, and we differentiate from here. It's much nicer because there's no more square root. So it'll be 2u du is a dt. Okay, so let's substitute. We have sine of u. What's dt? It would be 2u du over a is dt. So this a is a constant. Let's move it outside. 1 over a, okay? And we still have a 2 actually also, so 2 over a, and then times u times du. This is a classic integration by parts now. So as I was saying earlier, maybe you could just directly do integration by parts on this, but this, I for sure know, after we made the substitution, I for sure know this is integration by parts. So let me do it the tabular method even. So since I already have a u, let's call it p and dq. So I want to choose my u and dv. And I already have u, so that's why I'm using p and dq. So p, I want to choose as u, because we want to reduce the power. U, derivative of that is 1, derivative of that is 0. Okay? dq is what's left, sine u. We integrate just as many times. So minus cosine u, minus sine u. We go diagonally, and we alternate signs starting from plus. Okay, so it'll be, we go down the diagonal, so it'll be 2 over a times minus u cosine u. Okay, this becomes plus sine u plus c. Back substitute, u is square root of at. So it's 2 over a times minus square root at cosine of square root at plus sine of square root at, this is t, moment parentheses, plus c. This is my answer. Okay, so sometimes making a substitution, when it's a composite function, makes things more recognizable. Like this, I recognize as integration by parts. But as I said earlier, you might be able to just do integration by parts directly from here. It might be more tedious, but it might work also. I'm not sure. I haven't done it that way. So it might be a good exercise for you to try. Okay, next one is a challenging one. So I solved this one beforehand, and my first attempt didn't work. So let me even explain what I tried to do. So we have integral log of x plus square root of x squared minus 1. Okay, we have this integral. How do we go about solving this? Maybe as always, let's go down our techniques. Can we make a substitution? Maybe if we substitute the inside of the log, like how we did in the previous problem, inside of the sign, it's a composite function, so maybe that can help us out. So maybe let's try that. But let's go down the list first. By parts, it's to integrate log, that you have to use by parts. So I probably don't want to do that. Or maybe I have to. I don't know. We'll see. What was I saying? Okay, trig integral, clearly it's not a trig integral. Trig sub, I mean, there's a something squared minus something squared here, but then there's all these other terms. That wouldn't make it nice for a trig sub, so probably not that. Partial fraction decomposition is clearly not a rational function, so not that. Okay, so we have substitution maybe, and maybe by parts. It might not be nice, but we might have to do it. Okay, so let's do substitution first. As I was saying, maybe let's let u be, what's this? This guy in here. U is x plus square root of x squared minus 1. What would du be? Be 1 plus 1 over 2 square root of x squared minus 1 times 2x. Okay, so you can even simplify. It'll be x over square root of x squared minus 1. Okay? This should be a dx. Like this. Okay? This I clearly don't really see here. So this substitution probably won't work. Okay? I don't really want to substitute just this, because I don't think that will work, but let me try also. So we abandoned this already. U is square root of x squared minus 1. So remember, we can say u squared is x squared minus 1. So 2u du would be 2x dx, or u du is x dx. I just canceled the 2's on both sides. So what happens when we substitute here? Well, to get dx, it'll be u du over x. How do we get x? It'll be another square root, so I kind of don't want to do that. So let's abandon this also. So maybe we do have to use integration by parts. So it's going to be messy, but it's actually the way to do it. Actually, that's how I did it. Okay, so this won't be nice, but in the beginning it won't be nice, but it's going to solve the problem. Okay, so we let u be log of x plus square root of x squared minus 1. Okay? We have to let u be this, because if we put dv as it's the integral of this, which is exactly what we're finding. So we let u be that. Okay, so dv is just dx. That's the easy one. Let's do the easy one first. So v is x. How about what's du? We actually found it kind of up here already, but okay, let me write it. It'll be 1 over x plus square root of x squared minus 1. We need this first, and then we need the chain rule, which the derivative of the inside we found over here. So let me just copy it over. It'll be 1 plus x over square root of x squared minus 1 by dx. Okay, so our integral becomes, so it's uv minus v du. So x log of x plus square root of x squared minus 1. Okay, and then minus integral of, so let me write it like this. So x times this is how I'm going to write it. X over x plus square root of x squared minus 1 times 1 plus x over square root of x squared minus 1 by dx. Okay, so we have this confusing guy now. Did we get any better? Is integration by parts not the way? As I said earlier, it is the way. So what do we do? Okay, maybe let's combine this into one fraction, this 1 plus this guy. Let's make it one fraction instead of two terms. Okay, so everything else in the beginning is the same. Okay, minus integral. First term's the same. So to get this, combine this and this together, we need a common denominator. Here, for this 1, it's the same thing as square root of x squared minus 1 over square root of x squared minus 1. Okay, so it would be square root of x squared minus 1, and then we add it to this numerator, and then we have a common denominator, like this. Okay, is it much better now? It actually is. Hopefully you can see this cancels with this. And now it makes it a much nicer integral. Okay, minus integral x over square root of x squared minus 1 dx. This we can solve with a simple substitution. We can use u. We didn't use u anywhere yet. This is just using the definition. So we can let's use u. U is x squared minus 1 du 2x dx. Okay, so we get x ln of x plus square root of x squared minus 1 minus, we get half integral of du over square root of u. Okay, x log x plus square root of x squared minus 1 minus half times, what's the integral of square root of u? That is just 2 square root of u. Okay, and then plus c, this half and this 2 would cancel, and then we need to back substitute u. So that is, we're almost done, x ln of x plus square root of x squared minus 1 minus square root of x squared minus 1 plus c, and that's our answer finally. Lots of work for this kind of innocent looking integral. It looks simple because it's just one term, but it's actually complex because it's a composite function here. So the idea that we had of maybe substituting the inside would help, but it didn't help actually. So we resorted to integration by parts, just trying it out, and in fact, it did solve it. Okay, and it kind of makes sense because if you remember, integration by parts is derived from the product rule. So it's likely the derivative of something like this, something that looks like that, or maybe even this, if you remember the product rule. Okay, so do I have enough time to do one more problem? What's the next problem? Okay, I can do the next problem also. Let me squeeze it in here. Number 30. Integral -1 to 2, absolute value, e to x minus 1 dx. So how do we integrate this? The intermediate part is probably the absolute value. So maybe, since this is quite an easy function, let's sketch it out to see how it looks. So let me do it up here. We know how e to x looks. This is just shifted down by 1. So when x is 0, we get 0 because e to 0 is 1, minus 1 is 0. So, and then we have an asymptote. Remember, e to x has a horizontal asymptote at y is 0. Now it's shifted down, so the asymptote is that y is 1. So it looks something like this. Okay? So from minus 1 to, let's say 2 is over here, well, we see that from 0 to 2, it's above the x-axis, so it's going to be positive. But from negative 1 to 0, it's below the x-axis, so it's negative, but we want to take the absolute value. So remember how to do that? We have to flip the sign of the function. So we break this up into minus 1 to 0. This is where it's negative. So instead of e to x minus 1, we have negative e to x minus 1, like this. Or you can write it as 1 minus, without this negative sign up in front, it'll be 1 minus e to x. Same thing. I'll write it like this though. Plus integral from 0 to 2 of e to x minus 1. Okay? And now we just solve. Okay? This is just, okay, let me actually write it as negative 1 to 0, 1 minus e to x dx plus integral from 0 to 2, e to x minus 1 dx. I do like it like this better. Okay, so here, it's just x minus e to the x, evaluate from negative 1 to 0, plus e to x minus x, evaluate from 0 to 2. Okay, so fundamental theorem of calculus, we get 0 minus 1 minus parentheses minus 1 minus e to minus 1, okay, plus it'll be e squared minus 2 minus parentheses 1 minus 0. And this should be the answer. I'm not going to simplify. Okay, so that was the next few problems. Hopefully this was helpful, especially this one if you were stuck. I solved it for you, okay? And hopefully it was helpful to see that even I tried a few techniques before I resorted to the more painful one that did work in the end. All right, so don't be discouraged if you get stuck. You might, even someone like me who's done calculus for many years, been teaching it many years, so has to try multiple techniques sometimes. All right, please like this video if you found it helpful as always, and please subscribe also if you haven't already, and hopefully I'll see you in the next video. Bye.